Hello everyone. In this video we will discuss how we can find the time complexity of a recursive function using the recursion tree method. We will be utilizing the recurrence relation in order to construct the recursion tree. So some points regarding the recursion tree is listed over here. The first point is each node in the recursion tree represents the cost of a single subproblem somewhere in the recursive function invocation. Okay, so that is what is represented in each of the nodes of the recursion tree. It will be the cost of a single subproblem somewhere in the recursive function invocation. Then sum the costs within each level of the tree in order to obtain per level cost. So we will be adding all the cost in each level of the tree, so that will be giving us the per level cost. Then we will add all the per level cost in order to determine the total cost of recursion. We will discuss this using an example. So here I have a recurrence relation. The recurrence relation is T of n equal to 2T of n by 2 plus C, and this is applicable if the value of n is greater than 1. Otherwise it is just C if the value of n is equal to 1. Okay, we will utilize this recurrence relation to construct the recursion tree. When the value of n is greater than 1, I can draw a simple tree structure to represent the value of T of n. That is T of n, we can actually draw a simple tree. The structure of that simple tree will be something like this. That is, we will have a cost C, then we will have to solve two problems of size T of n by 2. Okay, so when you look at this tree structure, you can see that this is essentially representing this part of the equation. That is, we have a total cost of C. On top of that, you have to solve two problems of size n by 2. So the total cost will be 2 into T of n by 2. So if you add T of n by 2, T of n by 2, then C, you will get the value of T of n. Fine. Now what will happen if you want to find T of n by 2? This can also be drawn using the same equation. So if the value of n is n by 2, then this will be 2T of n by 4 plus C. So T of n by 2 will be, you will have a cost of C. Then you will have to solve two problems of size n by 4 and n by 4. So this is T of n by 4 and this is T of n by 4. What will happen if the input size is equal to 1? If the input size is equal to 1, then the cost is C. We will have something like this. We will have a cost equal to C and C whenever the input size is 1 of each of these subproblem. Then we will have to use a C in order to combine those two subproblems. So this C represents this C in this equation, and these two C's are when n equal to 1. Now we can form a complete tree structure from these simple tree structures. Okay, so I'm doing that. That is, in order to get the value of T of n, then so I will have a C. On left and right side, the problem size will be T of n by 2 and T of n by 2. And we have seen that for T of n by 2, again we will have a cost C, then 2T of n by 4s. So here I can write C and C. Then again I can have C and C. Here also I can have C and C. And these are the costs for combining the problems. And we can continue this procedure on and on. And we don't know how many levels it will go, but we are sure that at the end the cost will be T of 1. So this will be C, C, then C, 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 C and C. Okay, so these values are corresponding to the value of T of 1. Okay, so all this will be with value T of 1. Okay, so we have constructed the recursion tree. Now what we have to do is we have to add the cost of each of the level. Here I have the first level. The first level has only one value of C, so the total cost here is C. And here I have 2 C's, then the total cost is 2C. Here I have 4 C's, the total cost is 4C. Then you will have 8C, and all the way down we have several values of C. So in this level the size of the problem will be 1. So if you have n elements, then there will be n C's. Then only we will have the size of a single subproblem equal to 1. So we will have the number of C's here equal to n. Okay, so at the end I will have n C's. Now our job is to add all these values. So the total cost is T of n is equal to C plus 2C plus 4C plus all the way up to NC. Okay, So we have to find this sum. And if I take the value of c out, then I have 1 plus 2 plus 4 plus etc. plus n. Okay, so this is essentially a GP. Okay, now we have to find how many terms are there in this GP. In order to find the number of terms, you can just look at this particular tree structure. So here the coefficient of c is 1, here it is 2, here it is 4, next we will have 8. At the end we have the coefficient equal to n. Okay, so this is actually 2 raised to 0, and this is 2 raised to 1, this is 2 square, this is 2 cube. We don't know what this is, but we can write it as 2 raised to k. So this sum can be modified as c into 2 raised to 0 plus 2 raised to 1 plus 2 square plus etc. up to 2 raised to k. Okay, so this will be, so the sum can be written as c into, this is 2 raised to, we have k plus 1 terms, so we will be writing 2 raised to k plus 1 minus 1 divided by 2 minus 1, because the common ratio in this GP is 2, and this is c into 2 raised to k plus 1 minus 1 divided by 1. Okay, now this can be written as c into, what is 2 raised to k plus 1? 2 raised to k plus 1 is 2 raised to k into 2 minus 1 divided by 1, or this is c into, what is 2 raised to k? 2 raised to k is n. Okay, that is 2 raised to k is n. So we can write n into 2 minus 1, and this is actually c into 2n minus 1, or if you simplify it further, this is 2cn minus c. Okay, and if you find the order of growth of this function, you can remove any constants and you can also remove coefficients. So 2c is actually a coefficient, so this function will have a time complexity of big O of n. Okay, that corresponds to this value of n. Okay, now let's look at one more example. Suppose that I have t of n equal to 2 t of n by 2 plus n if the value of n is greater than 1, and it is 1 if n equal to 1. So this is something similar to the recursive relation for a merge sort, and we will have to find the time complexity of that function using recursion tree. And if you construct simple recursion trees, so in order to find t of n, you will have to have a tree structure where you will have a cost of n, then you will have to solve two problems of size n by 2. So this will be t of n by 2, and this will be t of n by 2. Okay, what if you have to find the time taken for solving a problem of size n by 2, then that is actually the value of t of n by 2. Then also you will have a cost of n by 2, then you have to solve two problems of size n by 4, so that will be t of n by 4 and t of n by 4. At the end we will have the size of the problem equal to 1, then the cost will be 1. Okay, now we will develop our recursion tree from these simple tree structures. Now in order to draw the tree structure for t of n, we have t of n as something like this. You will have a cost of n, then you will have to solve two problems of size n by 2. For two problems of size n by 2, we have to find t of n by 2 and t of n by 2. But t of n by 2 is a tree structure with root n by 2, then two tree structures of size t of n by 4 and t of n by 4. So here I can write the cost as n by 2 and n by 2. At the next level, we will have to solve problems of size n by 4. So for solving a problem of size n by 4, we will have a cost of n by 4. Then we will have to solve two problems of size n by 8. Okay, so here I will have a cost of n by 4. Here also n by 4. Here n by 4. And here also n by 4. And we will continue this procedure on and on. At the end we will have problems of size 1. So the cost will be 1, 1, 1. and these ones are written as per this equation. If we have a problem of size n equal to 1, then the cost is 1. Okay, so we have constructed the recursion tree. Now we have to find the per level cost. So the per level cost of the 0th level will be n, and here you have 2n by 2. So if you add n by 2 plus n by 2, you will have the total cost equal to n again. And here you have n by 4s, so in total you have 4n by 4s, so 4 into n by 4 will be equal to n again. So this can be written for several other levels also, and at the end, if you have a problem of size n equal to 1, then we will have n different problems. So the total cost will be 1 plus 1 plus 1 plus 1 plus etc. up to 1. So we will have n ones, so the total cost will be equal to n. Okay, now we have to add all these n values. Now the total cost T of n is T of n equal to n plus n plus n plus etc. plus n, but we do not know how many n's are there. Okay, so we don't know number of terms. So in order to find the number of terms, you can see that the denominators of these input sizes are varying with the power of 2. Here you have an input size n, so this can be written as n by 2 raised to 0. So this one is n by 2 raised to 1. This is n by 2 square. At the end you will have something like n by 2 raised to k, and this k is the number of levels of the recursion tree, and we have to find this value of k. To find the value of k, we should have n by 2 raised to k equal to 1, that is the input size. So if you put n by 2 raised to k equal to 1, then that implies n is equal to 2 raised to k, and if you take the log on both sides, you can find the value of k. So we are taking the log with respect to the base 2. Okay, so the value of k is log n to the base 2. Okay, so that is the value of k. So in total you can see that this is the first level, this is the second level, this is the kth level, and this is the 0th level. So in total we will have k plus 1 levels. Okay, so here we will have k plus 1 terms, or we will have the value of k is log n, so the total number of terms will be log n plus 1. So we have essentially log n plus 1 n's, so T of n will be log n plus 1 into n. So this is n log n plus n, and if you look at this equation, the leading term is n log n. So this is a problem of size big of n log n. Okay, so I hope the idea is clear. That is how to find the time complexity using the recursion tree method, and thank you.